So I would like to introduce you all to Professor Christopher Viney. He will be our guest lecturer for our class today. Uh, he is a founding professor at UC, University of California, Merced, and he also a professor in chemical and materials engineering at UC Merced. Please welcome Professor Christopher Viney. Yeah.
Hello, or good morning to you. It is evening here. We're 13 hours behind, but I hope you are having a good morning. And thank you for the opportunity to work with you today and hopefully introduce you to some, what I hope you will find interesting ideas about patterns and irregularities. I am going to try and share my screen. Let's see what happens today if I do that. And it's moved forward a little bit too far, but there we go. So that's the first slide. And I'm going to try and put this into full screen, at least from my end, and then hopefully it will also be sort of full screen at yours. All right, and Vipawi, please tell me if, when I start talking about words, if you don't see the words, please complain.
Yes, I can do that.
We had a slight technical problem for about 5 minutes yesterday, but all was well. And Vipawi heroically was describing what I was saying without actually being able to see my slides. That was very impressive. So what you see here is a picture. There is some pattern in there. And so there's an example of a pattern. And if you look at this sort of dark purple grayish grid, you see some rectangles, and maybe there are more rectangles, but they're disappearing off to the sides of the picture. And then you see a whole network of sort of squares. They're not really square, but they might once upon a time have been squares, and with a lot going on in there. And so what you see is actually a combination of regularity or pattern together with some irregularity. And I hope you agree that if it was all pattern, you might not find it very interesting, but it's all the irregularity and the things going on that perhaps make it a little bit more interesting. If you're wondering how this picture came to be, what you're seeing is a reflection in the glass wall windows of a building. And so the glass is supported by the metal purple rectangular grid. That's actually support holding the windows in place, the reflective surfaces. Reflected in the surface is a building that's actually behind me when I took this photograph. And there is a sunset being reflected in the windows of that building that is behind me. So what you're seeing is a sunset reflected in a building, reflected in another building, caught by my camera. So yes, there was a bit of planning involved. I didn't plan the sunsets, but I was walking through campus. I saw this very interesting reflection in the building, and I thought, my goodness, I have to get a picture of it. Luckily, I had a camera with me. So patterns and irregularity, we're going to talk about both. So you already know what the title of the talk is, and Vipawi looks happy, so she can probably see my new slide. Good. So pattern and irregularity. You know who I am now, you know where I work, and I'm sure you know that it's January 2025, so we don't have to spend very much time on this slide. So what I'm going to do is talk about a little bit about the attributes of a pattern, because if we're going to have this conversation about pattern and irregularity, I think we have to try and figure out that we all have some agreement about what we might mean by pattern. So this slide here will talk about some of the attributes, some of the characteristics of a pattern. What makes a pattern a pattern? Later, after I've talked about pattern for a little bit, I will also have some slides about attributes of irregularities. So patterns for now, and then the irregularities will creep in. And I hope to eventually demonstrate that patterns can be a lot more fun when they have irregularities in them. They're a lot more interesting and perhaps a lot more stimulating. So what can we say about patterns? Well, sometimes a pattern is just a fancy word for something that is familiar. So we know something and we want to describe something else, and we use the word for something that we know to describe the something else. So pattern, I think a lot of people think of a pattern as being a repeating structure. Like if you buy a whole sheet of stamps at the post office, there's a whole sort of lattice of stamps. Well, that is, yes, it's a pattern. That's the stamp repeats itself in 2 dimensions on the sheet. But a pattern can also be if you have, perhaps if you are doing something like making a dress, for example, you're making some textile. You go to the store, you buy a pattern, or maybe your friend designs a pattern, and then you try to make a copy of that when you work from that pattern to make your version of that same thing. So yes, there is copying, but at one time there might only be one of them, rather than a whole lot of repeating copies of them. But one pattern can then be, so it's like a mold, perhaps. Think of it a pattern as being the mold for making more of the same thing. And this can be useful actually, because maybe you see some shapes in the clouds, and you look up, and maybe you're in the park and you're sitting down having a picnic, and you look up at the sky, and you see a cloud, and you don't know quite how to describe it, but you tell your friend, look at the cloud, it looks like Mudang, right? And everybody knows that what this cloud looks like, because there are many different kinds of cloud. There's only one kind of Mudang, as far as I know. And I probably a little bit bigger than the last time I saw a picture. um, or if you look in the sky at night and you see the stars make patterns. And historically, people in many different cultures, I know the ancient Greeks used to do it, the Babylonians did it, and I'm sure, in Asia, people were looking at the sky and seeing patterns and using familiar words to describe the patterns. So that's a simple way of looking at a pattern, but more usually, I think we imagine some regularity. So there's some sort of periodic structure like you find in a crystal. In a crystal, the atoms are sitting on a lattice. And if you tell me where an atom is, I can tell you how far you have to go to get to the 100th atom away from there, if the crystal is big enough, or maybe the millionth atom. It's very predictable where you'll find those atoms. Or if you're using a ruler, it's very predictable. If you have 1 centimeter, well, you know how far to walk along the ruler to see the next centimeter and the next one. And this is a very good thing, because can you imagine some joke ruler, a ruler that's just a joke, where all the separations of the markings were all different? That would be a terrible ruler, though it could make life perhaps a little bit interesting. In the same way, if you had a clock and the spacing between the seconds on the dial was not the same for all the seconds, that could be quite a difficult clock. Again, there might be some humor involved, and you could play a trick on your friend and change what the clock looks like, but it would not be very useful as a device for telling the time where everybody can agree on what that clock is trying to tell us. So regularity can be important. And in a sense, if it's going to be regular, it's going to be dependable. You can depend on something that is regular. And humans all over the planet, people for thousands of years, have relied on the dependability of the progression of seasons. You expect that spring comes after winter, and summer comes after spring, and autumn comes after summer, and winter comes after autumn, and then there is another spring, and you go round that cycle. You depend on that. And if the winter is wrong or the summer is wrong, maybe people won't eat because the seasons don't work, then crops don't work, and then difficulties can arise. So some sort of pattern, we look for patterns. We are programmed to look for patterns in life. Life cycles. You plant something, it grows, you harvest it. You raise an animal, you raise a chicken. The egg turns into the chicken grows. Maybe you eat the chicken, or maybe you use the chicken to produce more eggs. But there's a cycle involved. And again, very, very fundamental to our survival as human beings. Or if you are a fisherman, you depend on the tides, and you have to understand the predictability of the tides so the boat can go out of the harbour safely and return to the harbour safely. And you know when to fish. And All these cycles that make life possible and make life predictable. And a very modern example now, quality control and failure analysis. So, if you go to the store and you buy a light bulb, you would like to be fairly certain that when you come home with the light bulb, it's actually going to work. You don't want to go to the store very often and find you have a not very good light bulb. Most of the time, you expect it to work and to last for a long time. And you expect that it to last for, you don't want one light bulb to last for 5 minutes and another one to 5 days and another one for 5 weeks. You want them all to be predictable. And if they're not going to be predictable, at least you want to not a huge variation between the lifetimes of your light bulbs. So again, dependability is important. And slightly different meaning, but related to dependability, is predictability. What will happen in the future? And that is something, of course, humans really, sometimes people pay money, they go to a fortune teller because they hope the fortune teller can tell them what the future is. That is generally not money well spent because we don't have really many mechanisms for predicting the future accurately. The only things we can predict about the future is that the sun will come up tomorrow, and we can predict where it will come up, and we can predict how the sun will travel through the sky because of how the Earth rotates and where the sun will set. And so some things are predictable, but if you can find a pattern, that helps with the predictability. And so people, again, over thousands of years in some cases, they saw the sun disappear. It was an eclipse. Didn't happen very often. And sometimes it didn't happen in a particular part of the world. Maybe it doesn't happen more than once in a lifetime. Or maybe never happens in a lifetime. And so people hear from their grandparents that, oh, there was a time when the sun went completely dark for 5 minutes and everybody was terrified. Well, or a comet appeared in the sky, and for thousands of years, comets that appeared in the sky were a source of usually alarm because nobody really understood what they were, but they generally thought people thought comets were bad luck. They never really thought that they were good luck. But now that we understand how these things work, we can predict them. And so the fear has gone away, and the ability to predict and be able to be comfortable with these sorts of events has greatly increased. So it used to be you just had to go by historical observation and word of mouth and stories that people told. But predictability is hugely enhanced by science and technology. And of course, you are students in science and technology, and so you are used to being able to predict things. So if you're looking actually at my background picture, you will notice, and let me see if I'm going to position myself. So if you look right above the top of my head, you'll see a red ball in the sky. The building behind me is part of my campus. I'm not actually there at the moment. It is evening here. It is later evening than you see in the picture. I'm actually at home on a computer. But the background picture shows my campus with that red ball in the sky, and that red ball is an eclipse of the moon. And so the moon goes this dark red color during a total eclipse. And fortunately, because we can predict these things, I knew where I needed to be to take that picture, because these things are predictable. Okay, well, here is an example of a shape in a cloud. And if I hadn't said it was a cloud, I think most of you would have probably said, well, it looks like a cloud. But imagine, I saw this is a photograph that I took. And I saw this cloud. I saw this cloud and I was sort of surprised by it. And I thought, my goodness, that's rather unusual. And I came home and I told my family, I saw a cloud that looked like a spaceship. Now, imagine 300 years ago, did people understand spaceships? I don't know what they would have said if they come home and see that. They could not have taken a photograph of it, but they would have to find words that has the pattern, the shape, the characteristics of, well, in our language now, a spaceship. Now, one thing I want you to realize is that the scale at which you make your observation is very important. So if you're looking for patterns, or if you're looking for words or describing, what scale is this phenomenon happening on? Because this picture is actually the scale on which it was happening. And so yes, you can still see a little spaceship, But it's rather small in the big picture of things. It was just at the top of this enormous thundercloud, maybe about 25 kilometers from where I'm sitting now. It was in the same county here in Merced County in California a couple of years ago. Um, and yes, spaceship, but maybe not quite as big or as close as it would look in the first picture. If you really want to be technical, perhaps you want to know a cloud like that is called a lenticular cloud. And lenticular has the same word origin as lens, like you have a lens for making a spectacle lens, or a lentil, which is a sort of food. So lens, lenticular, lentils, all the same sort of thing. Let's have a look at an example of looking at constellations where you look at the sky. And there's a constellation in this picture. Some of you may recognize it. Does anybody recognize it? Anybody? Anybody? I can't see the chat window at the moment, but if somebody puts it in the chat, maybe Vipari can tell
Yeah,
me.
I can look. Anyone wanna guess? Do you familiar with this constellation or like the star pattern?
I know that you can see it in Thailand.
Oh,
It is visible in your sky.
yeah, I saw this the three uh straight line of the star in the sky. Yeah.
So is my
Yeah, that
cursor
part.
visible?
Yes, yes, that
Okay,
part.
so that is the belt. That's his belt, and this is his dagger. And right here, where you see this thing here is the nebula. It's a very famous nebula. So you put a small telescope on it, and you can see cloud. You see sort of pink and blue clouds, and very beautiful.
Mm.
I even managed to get a picture with my camera, but it's not in my talk today. But has anybody answered the question? Anybody know
Yeah,
what?
yeah. One student said Orion.
Yes. Well, good student. And I expect other people might have known it, but people can be very shy sometimes. And so, but yes, this is Orion. And so here, now I've rotated him really 45 degrees counterclockwise. Okay, so take Orion, rotate him 45 degrees counterclockwise. And in the background, you can see a superposition of the figure, the mythical figure of Orion. In Greek mythology, he was a hunter. So you see, so he's got a big club that he's raising up a club. I don't know what he's going to go and hit, but he's definitely hunting. His body is marked out by the four sort of big stars here on the trapezium, his belts, which are the three stars that Viparu was mentioning, and his dagger, his knife here, you can see is where the Orion Nebula is. And so if you look at the names of the stars, many people know about Betelgeuse, it's a very red star. It's been in the news recently because its brightness seems to be changing rather erratically. And so people are wondering, of course, it's a long, long way away, and the light we see now, of course, left it a long, long time ago. But astronomers are wondering if something interesting is going to happen, or happened a long time ago. But Betelgeuse, you can recognize it's very red. Rigel here on the opposite corner is very blue. So it's a very, very hot star. Betelgeuse is big and red, and Rigel is sort of not quite so big, but very, very much hotter. And all these stars that are labeled, I've got a list of them here. I collected some data from Stellarium. You can have fun with Stellarium. It's a program, runs on a desktop. They have it for Mac and for PC and for Red Hat and Linux and all these different platforms. And it's basically a planetarium. You can put where you are, and I know there are apps as well. There are other apps that you can do on the phone, but Stellarium is very powerful, and it gives you some really quite detailed planetarium experiences and a lot of data. And if you look, so I collected here this table shows how far from Earth in light years these different stars are. And why am I showing you this? Because Orion, he might look like a hunter if you have a really good imagination, and probably drank too much caffeine, because I think you need a really good imagination to see a hunter when you see all. So I don't know if people were like really, really tired, or had a lot of caffeine, or how they were driven to see a hunter in all of this, but good imagination, certainly they were creative in one way or another. Um, but notice it's a two-dimensional effect, because all these stars, they're not sitting at the same distance and making a planar pattern. There are huge differences in the distance. So, the closest one here at 252 light years compared to 1977 is a factor of about 4 difference in the distances. So from us, so a huge difference. So I'd like you to remember then that perspective matters. Okay, when we looked at the cloud, we saw that scale matters, but also when we look at anything, perspective matters. And we have to remember we may not be seeing the full three-dimensional consequences of what it is that we're looking at. So that's talking about the sort of patterns in clouds and the patterns in the sky. Let's look more at now some more sort of down to earth and perhaps more sort of mathematical patterns. So I'm going to talk you through a couple of examples of that. And people who like playing with numbers, I am actually one of them. Why? Because it's fun. I'll give you some other reasons in a few minutes, but hey, it's fun. So when we talk about a prime number, I imagine you all know what a prime number is. Just in case, reminder, a prime number can be divided by only 2 things exactly. Number 1 and itself. So the only factors, if you will, of 31 are 1 and 31. That's it, none others. And by factors, of course, I mean whole numbers. Okay. So then you put a 3 in front of it. Instead of 31, you take 331. It's also prime. You look at 3,331. Oh my, it's prime as well. You look at 33,331. Hey, it's prime. You start saying, well, is this forever? Can I put another 3 and another 3 and another 3? Does it go on and on and on? Can I prove it for the general case? For let's say X number of 3s, can I prove what's going to happen? Actually, I can't. And it's not just because I'm limited, I'm not a mathematician, but nobody can yet, is the interesting sort of observation. But if you get up to having, well, 4 3s followed by a 1 is prime, 5 3s, 6 3s, 7 3s, but you get to 8 3s followed by a 1 and you discover it's not prime anymore. No, and people actually studied this before calculators. So somebody had to be very patient doing this longhand, okay, on paper with a pencil. And then the next one, where you've got, how many do we have? That was 8, so now you've got 9 3s. That's not prime either. Or 10, or 11. So maybe we ran out, maybe only the first 4 were primes, and now we've run out of them. What do you think? Actually, you go this far and it's prime again. All right, so what do we have? 3, 6, 9, 12. We've got 17 3s followed by a 1. It's prime. And so, it's very frustrating actually, because you think you see a pattern, and then maybe you think you see a different pattern, and then, so quite often with numbers, finding patterns is actually, there's a whole area called number theory where people try to do this. And is there a pattern in how prime numbers of this type are distributed? So a pattern of how the distribution works? No, nobody's even found a pattern for that yet. So it remains a mystery. Now, I'm not saying that you can never find a pattern, it's just that nobody has. Okay. And that's what makes number theory so interesting, of course, is because if you could prove a pattern, you would be instantaneously very famous. Here's another mathematical example. N, an integer, squared, minus n plus 41. Is it prime for all integers n? And if you start playing with these, yes, it seems reasonable. So let's make a table. N and n squared minus n plus 41. N is equal to 1, you get 41. N equals 2, you get 43. And then 47, 53. Up to number 8, they're all prime. Well, that's a longer pattern. In the previous slide, we only got 4 primes, and then we sort of ran into trouble. Well, you get into 8. You can go all the way out to 40. All of the ones in between, from 8 all the way out to 40, they're all prime. And then you get excited, but you shouldn't. You should not be excited, because if you look at the original equation, you realize, well, if n was 41, then I've got a 41 in each of those places, so the whole thing's going to be divisible by 41. So it must run out at 41. If it hasn't run out before 41, it must run out at 41. What about the next ones? Is there a pattern? Well, it would take some work to prove it. I don't think that's going to be your homework. I hope not. It can be rather difficult. Here's another example, what are called Fermat numbers. So Fermat himself, now Fermat, very famous mathematician. Some of you might have heard of Fermat's last theorem. Okay, so Fermat's last theorem, we know that by Pythagoras, you can sometimes find integers where the sum of the squares is equal to another square. So, 3 squared plus 4 squared is 5 squared. 5 squared plus 12 squared is 13 squared. And what he said, what Fermat actually said, his famous theorem was that you can't do the same with cubes or power 4. You can't take an integer and raise it to the power 3 and add another integer and add to the power 3 and get something that is an integer to the power 3. So it only works for n equals 2 and 1. That's his famous theorem. It took hundreds of years for someone to prove it. It was actually a British mathematician just proved it about 20 years ago. But so that's what Fermat is perhaps most famous for. There were books written about that theorem, but he was also very successful at number theory, and even Isaac Newton was impressed with the work that Fermat did. And one of the things that Fermat here, so he thought that if I take 2 and I raise it to the power of 2, which itself is raised to some integer number, and I add 1, that result is always going to be prime. Well, he did it with 0 and 1 and 2 and 3 and 4, and notice how quickly big the numbers get. How big they get, very, very quickly here. And so imagine you don't have a calculator now. What's the next number is going to be absolutely huge. How do you prove? And I think he got lazy at this point and just said, well, I think they're all going to be prime. And it took Euler. You've all heard of Euler, I'm sure, another famous mathematician. 100 years later, he showed, just imagine how difficult that was, to show that 2 to the 2 to the 5 plus 1 is equal to these two numbers multiplied together. Now, I don't think he didn't divide first of all by 2 and then by 3 and then by 4 and then by 5 and go all the way up to 641. I don't think he tried it. I think he actually had a more elegant proof than that. So all other numbers of this type that have been studied are composite. No other prime one has been found. But we don't know that no more primes exist. We have no idea. Again, you can be very famous if you can prove them. Why am I telling you these examples? Because be careful, you can't be sure of a pattern just by looking at it. Sometimes you can, but often you can't. So don't get too excited about the pattern until you've thought about it or explored it. And sometimes the most you can say, it's a pattern up to this point, and beyond that, we don't know. It's good to admit when we don't know. Okay. So I've been giving you some examples of patterns in numbers, or maybe not quite patterns in numbers. That is the point. Why do we care? Why are patterns in numbers important? Well, sometimes we can care just before intellectual fulfillment. It's a bit like, why do people climb mountains? They're there. Why do we study numbers? We have them. They're there. They're free. You don't have to pay to get these numbers. You can just go and work with them, right? They give us something to do. There is joy in discovery. Joy in discovering patterns, or sometimes the irregularity in the pattern. You see, the patterns only work to a certain distance. There's where irregularity kicks in. It's really good mental exercise. Absolutely, encourage you to, I think And I'm an old person, so of course I'm going to feel this way, but I think we spend too much time using our calculators and maybe not enough time thinking. So when when I was a student, I used to go to the grocery store. I liked to be able to hand the cashier the exact amount of money that my groceries cost. Because while I was walking around the store, I was adding up the numbers in my head. And I think that was, I'm not saying you all have to do exactly that. What I'm saying is find reasons to play with numbers. It is a good exercise. Okay. Some people look at it from the aesthetic point of view. Why? Because patterns and numbers, they think they're beautiful. Now, if you're enjoying yourself, you think they're beautiful. If you're getting frustrated, you might not think they're beautiful. But there is a certain aesthetic there for people who look for it. Now, for all of us, it's useful. We all depend on patterns and numbers because number theory is actually the basis for a lot of encryptation. And so when the data are encrypted for transmission over the internet, and it might be a bank transition, or it may be a purchase, or it might be personal data, but the encryptation often involves the use of numbers that are difficult to factorize, or that might be large and prime numbers. So this sort of knowledge and these patterns are actually the basis at the moment of cryptology in computers. Now, when we get to the idea of quantum cryptography, where computers can basically look at all possibilities at once, we might have to find even more advanced ways of actually doing the encryptation. But anyway, I just thought I'd share with you why it's fun and why it's necessary rather than just a source of patterns. So I promised about 15 minutes ago that I was going to, maybe a bit more than 15 minutes ago, that I was going to also look at some attributes of irregularity. So let's do that. We've looked at some attributes of regularity and pattern. Let's look at irregularity. The word itself is often, here's an English word that maybe some English people don't actually come across very often. It is pejorative. If something is pejorative, it can have and generally has negative meanings, negative connotation. So pejorative, it's something that isn't good. So impurity, defect are quite often synonymous with irregularity. And I want to encourage you not to think that way, not to think of irregularity in a pejorative sense. Well, for one thing, you're stuck with them because in physical materials as well as in real life, irregularities, impurities, and defects are inevitable. We are stuck with them. Okay? There is no such thing as perfection on earth in real life. Be kind, all right? If we can characterize the irregularities, here they are, we're stuck with them. Okay, we may as well try and understand them. Let's study them. Let's see what we can learn. Understand their origin, their prevalence. How many are there? How frequent? How common are they? How uncommon are they? How do they behave? What are their characteristics? If we can understand all that, then we can start to maybe control them and then perhaps even benefit from them. And so I've got some examples here. Metal alloys contain desirable amounts of impurities. We still call them impurities. We could call them alloying elements, but quite often they're still called impurities. But they're very necessary. So you can put a little bit of copper into silver, and you make what is called sterling silver. And sterling silver is much more, it's harder, it's more wear resistant, and it's more tarnish or corrosion resistant than pure silver. So that's why a lot of jewelry is made out of sterling silver. The impurity is useful. Or the difference between cast iron and steel is actually the carbon content, and the difference between many different kinds of steels is, to a large extent, the carbon content. Carbon is the impurity, but my goodness, it's important in the properties, controlling the properties of steels. And then if you work with semiconductors, okay, electronic devices, semiconductors, the electronic properties of semiconductors depends on small amounts of impurities. And so you put gallium into silicon to make a p-type semiconductor. You put arsenic into silicon to make an n-type semiconductor. if you have a p-type semiconductor and an n-type semiconductor, you can start making diodes and transistors and all the wonderful electronic devices that we depend on. So you see those impurities, not only are they, it's a bit unkind to call them impurities, but they're actually indispensable. Very, very important. I'm glad we have them. Okay, so they are necessary. And our job then is to find out which ones are good and how many of them. You can have too much of a good thing, or you might not have enough of it, right? So here's an example of necessary irregularities. And this picture you often find in textbooks, in materials science textbook, mechanical engineering textbook. You see these sort of pictures where you take in the solid state one metal, a piece of one metal, and you put it right next to, with a very nice a nice flat interface next to some other metal. Okay, in this case, copper, which is sort of copper colored, and nickel, which is sort of nickel colored here. And you put them together, and after some time, the copper moves into the nickel, and the nickel moves into the copper, and you get an alloy. And if you heat it up, it goes a little quicker, right? You can speed this up by heating it. Or squeezing it will also maybe help it. But this picture, and you see it in so many textbooks, it is very, very wrong. There is a problem with this picture, let's put it that way. Does anybody notice the problem, or does anybody able to comment on it? And interestingly, yesterday when I asked a question, and Viparia was doing the translating, but she also got the answer right. I wasn't actually asking her, I was asking the students, but she answered it herself because class didn't answer it. So I wonder if this class maybe wants to answer. What's wrong with this picture?
Yeah. Anyone wanna try? You could make a guess. Mm. And remember, he mentioned that this is like solid state. So, um, if you imagine about it, you might know the answer. Mm.
If you had a class on introduction to materials, if you ever had a class somewhere, then I hope maybe they might have had to show you a textbook with this picture, but I hope the professor explained what's wrong with the picture. I'm not seeing anything in the chat.
Yeah, I don't see it. Or you
I
could
don't have,
guess in Thai too, if you know in Thai, if you think
yeah,
in Thai. Mm. I could translate. Mm.
I don't have the chat window open, but I can see there's only one comment in the chat, and that appeared a long time ago. So anybody? Nobody? Well, you're going to make me do all the work here, aren't you? Okay, well, how do the atoms squeeze past each other? How do they squeeze past each other? They're approximately the same size, and you can't move one atom through another atom. That's not going to work. And so really what you actually need are some gaps. You need some missing atoms in order to move the other ones around. And a missing atom is called a vacancy. Okay. Here's how you can visualize it. So you've seen puzzles like this, I think. You can get toy puzzles, and sometimes it's numbers, sometimes there's a picture, and you reshuffle the pieces, you can recreate the picture. Well, I took one of my pictures, cut it up into little squares and shuffled them. So what you're seeing here is the shuffled, the disorganized version of the picture. But if I make this into a puzzle, the only way that you'd be able to solve the puzzle is if I leave one of these blocks open so that I can, because one way you can think of it as moving the blocks around, or maybe you can think of it as just moving the vacancy around. But something's got to be able to move, right? So if I shuffle this and then solve the problem, it should look like that. Okay, so I go from this, which is a mess, to that, which has some patterns in it, right? Look at it. And what I will do is the next slide just shows, I've taken away the word vacancy and just made it a bit more transparent so you can see what's underneath it. If the whole picture, of course, when I took the photograph, there wasn't a hole in it. I had to make the hole artificially. Yeah. You're looking at another eclipse of the same moon, different eclipse, same campus, still my campus here in Merced, California, but I'm photographing it through an array of solar panels. So now you can think about the ideas of a pattern of solar panels, an eclipsed moon. The solar panels are dark, and so is the moon. So you can think of there's several messages in that description. All right, well, let's look at some defects in metals. Okay, we actually just impurities, as we call them, or solutes, things dissolved in the metal, solutes, or alloying elements, all the same thing. We realize those are useful. But you can also get structural defects in the crystals of metals. So what I've got here is a very oversimplified lattice picture, very oversimplified. There's only one metal that actually has this structure. So if any of you have ever studied crystal structures, this is what's called simple cubic. Okay, it's not body-centered. There are no atoms in the middle of the cubes. It's not face-centered. There are no atoms in the middle of the faces of the cubes. It's just simply atoms at the corner of cubes. There's only one metal which is what's called simple cubic, and I hope you don't have any because it's polonium. It's rather dangerous. It's radioactive. Okay, but it works. The simplified structure here works fine for telling a story. What you notice is there's a mistake in my crystal. You see, where it says edge dislocation, the arrow points to the atom here where it says edge dislocation. That atom doesn't have anything joined to it underneath it. Look at every other atom. There's an atom on top, one below, one on the left, one on the right, one back, one at the front. But this one has nothing below it. And there's a whole row of atoms like that. And such a defect with this sort of geometry is called an edge dislocation. And if a dislocation can move easily, the metal is soft and ductile. You can shape it, you can pull it into wire, you can beat it into a sheet. Okay, you can shape it easily. If the dislocations cannot move, the metal is strong and brittle. So you see, the metal, it's not just going to give you some behavior because of what the ingredients and the impurities are, but it's also going to depend on the actual structure and whether there are defects in the structure of the metal. So if you can move the dislocation, easy, metal is soft. If you can't move the dislocation, not so easy, the metal is strong. Show you some pictures here. So here is, and there's no edge dislocation yet in this picture, but we'll get one in a minute. And so if I want to shear the metal, so I'm pushing the top part of it to the right and the bottom part of it to the left, like those arrows suggest. And so instead of sliding everything across at once, moving the top and the bottom, breaking all those planes and sliding everything at once, I just do it with one. You see, and it just moved over a little bit. And a little bit later, you see, there it is now. It's broken off, and it's sort of starting to nudge up against the next plane. Now, the next plane is breaking, whereas the first one that came along is starting to join. Okay? You see, you've made a little step. And the dislocation, you can see it very clearly now. And one step at a time, instead of sliding the whole crystal, I just have to break one row of bonds at a time. So much easier. The material is so much softer. Okay, there it goes. I've taken it halfway. Then I got tired of drawing this diagram, so I took it the whole way. Just in one big step at the end there. But you see, the whole metal has eventually slid, but one row of atoms at a time. Doesn't require so much energy. Material is softer. Now, sometimes if you animate this sequence and you watch that one half plane move across, it looks like an elephant actually is sort of eating grass. It's an elephant walking across the landscape, and the trunk. If you look at that half plane is the trunk. It's just sort of browsing along as it goes. So you see, and I've just used a pattern again. I used the pattern of the elephant to describe the motion of this. It's not a repetitive pattern, but it's a pattern that you can perhaps understand the visual image, you see. So another example of defects in metals is the grain boundary. All right, now I have to tell you a little bit about what a grain is, and if you know what a grain is, you'll understand why it has boundaries. So let's look at the grain first. So if I give you a piece of metal, maybe think of the building you're in. Maybe it's got some steel. I don't know where everybody is. Maybe you're at home, but if you're on campus in your lecture hall, there's probably some steel in the structure somewhere, and those steel beams. Each piece of steel consists of many, many, many crystals of steel, iron with carbon dissolved in it. And those crystals are quite small. They're typically micron sized, they're not centimeter sized, they're sort of micron sized, 10 micron sized, that sort of thing. You need a microscope to see them. Because imagine when you start with a liquid metal and you cool it, it doesn't just make one crystal that grows and takes up the whole space of the metal. Several crystals appear at once. Same as if you make ice cubes in the freezer, you put the liquid water in a glass or in a tray into the freezer, and you see many crystals starting to form. It doesn't just start at one point and spread across the whole glass. So the boundaries between these grains, grain is another word for crystal in this language, and so the boundary between grains, you can imagine the atoms are not quite as well joined up at the boundary as they are inside the grain. So the boundary is a defect. Okay, it's an irregularity. Okay, you're sitting in a nice, beautiful, organized crystal, except the crystal's not that beautiful because it's got some vacancies in it and it's got some impurities in it. And then you get to the boundary and you found yet another irregularity, right? Now, what do you think happens to dislocation when it arrives at a grain boundary? Let's go back to this picture and imagine that the crystal gets to a grain boundary. The dislocation gets to a grain boundary. What happens? It gets stuck because the crystal has ended, so that dislocation can't go anywhere. So can you see that if I have a lot of grain boundaries, which means I have tiny grains, more boundary, it's going to be stronger than if I've got large grains, because there are many more opportunities to get in the way of dislocations. Okay, so there are the boundaries. And if dislocation gets to a boundary, it gets stuck. All right, so that strengthens the material. Except if you do this at a high temperature, think those boundaries are where the crystals really don't join up that well. So it's fairly easy to melt, really. The metals always melt from the grain boundaries inwards. The grain boundaries melt first, and then the middle of the grain. So you go to high temperatures, and you can slide the grains past each other. And so at high temperatures, big grains are actually better than small grains. At low temperatures, small grains are better than big grains, if you want to strengthen the material. There's an equation that you learn in material science which basically says small grains are good, and it even relates the strength to the grain size. But then the trick question is, well, what happens at high temperature? It is completely the opposite. Okay. So again, just because you see a pattern, stop and think, does it always apply? Does it have limitations? So at low temperature, here are some words to help you. Okay, at low temperature, grain boundaries are obstacles to dislocations, and you strengthen the metal. At high temperature, grain boundaries slide easily, the metal is weakened. So this is very important because in a jet engine, okay, and even it doesn't even have to be like a jet engine like in a plane. It could be just a jet turbine used for generating electricity. So it could be something that burns fuel and runs a turbine. Could be in a ship. Ships are actually run by turbines as well. But the aircraft one is the best example, because when things break on a ship, you don't fall out of the sky. When things break on a plane, there could be a problem. So it is critical that people understand this in the aircraft industry. And when jet engines for aircraft were first developed, they were developed in the 1930s and implemented in the 1940s, a long time ago. The blades on the turbine, so you can think there's a central disc with a whole lot of blades sort of sticking out from it like a fan, right? And the blades, people made them by casting a liquid metal. So you cast a liquid metal. Now remember what I said earlier, when you cast a liquid metal, it doesn't solidify as one single crystal, it solidifies as lots of grains. And now you make a jet engine out of this thing so they get hot. And all those grain boundaries, they start to melt and they start to slide. And so those jet engine turbine blades only lasted maybe for a couple of 100 hours. So after 200 hours, the plane has to sit on the ground, completely replace those parts of the engine, because they will have stretched and the engine's dangerous to use now. So then people began to realize, well, if we can somehow make it so that the crystals grow along a temperature gradient, so when you solidify, you have a temperature gradient, and so they grow in a particular direction. So this, you can see and actually I'll just throw a microscope on top of my picture here. So the crystals in the middle picture, they're elongated. Now, of course, the boundaries which are perpendicular to the length of that blade are the ones that are going to fall apart the quickest, but you've minimized those by the orientation of the grains. And so these blades lasted much better, much better. And then somebody came along and said, well, maybe there's a clever way that we can grow the whole thing out of one crystal. There's an interesting bit of technology about how do you make an entire turbine blade out of one single crystal, but it's not our job to talk about that today, but I'd be happy to explain it under a different heading. But people have figured out how to make a single crystal turbine blade. And so these are the ones which can run for longer, and they can run hotter. And hotter is good, actually, in a jet engine, because the hotter you can run the engine, the more fuel efficient it is. The more efficient the engine is. And those of you who've taken a thermodynamics class will know something about the bigger the temperature difference across the engine, the more efficient it is. You've probably learned that somewhere in the thermo class. And also the pollution is not so bad, because if you run it hotter, the combustion byproducts are actually cleaner. You don't get a lot of nitrogen oxides, for one thing. So that sort of brown smoke, you get less of that sort of brown, smoggy smoke if you can run the engine hotter. So you see, an understanding of defects really does become, and the ability to manage those defects really does become very important. And I've only got one more slide here, and this is, I know you're a technology class, but this is it's technology students, but it's a general education class. And so, why do we do Gen Ed? Well, because it's good for you, right? General education helps us to think, helps us to be creative, helps us to get along with other people, helps us to have interesting conversations with other people, right? And sometimes you take two ideas from very different fields and put them together, and something completely new and startling and useful might come out of it. So general education is important. And so in that context, I'm just going to talk about irregularity and aesthetics. And so I sort of floated the idea earlier, but I'm going to emphasize that irregularity can add beauty. Okay, we realize it adds functionality, and it's inevitable anyway, but it can add beauty. And so when a bird sings, okay, so birds sing, right, and Twitter, whatever they do, right, but they make sounds, and they communicate with these sounds. And so if you study the bird song carefully, you realize that it's not a very exactly repetitive pattern. There's pattern there, but there's pattern with irregularity superimposed on it. So what we have here is some work. It's from a friend of mine who was a professor of music at Cambridge University. He taught music at one of the colleges. And what he did is he would use a recorder, and this was a long time ago, so I was young and he was sort of middle-aged at the time, and he would use a tape recorder, good old-fashioned tape recorder, and a microphone, and record the birds. And specifically what you're looking at here is the song from a woodlark. Okay, it says woodlark here. You do not get woodlarks in Thailand naturally. Maybe you have them at zoos, but it's not naturally found in Thailand. And he recorded and he slowed down so that he could then write on musical paper, write the notes. But you have to slow it down so it's not such a high pitch, and you can also hear the differences between the notes. And this is what he wrote. He just copied. Okay, so copyright woodlark. Yeah. Okay. This is not human composition. He just transcribed the woodlark. And you notice, here's a group of notes, and a very similar group of notes, and a very similar, and you notice the gaps are sort of similar, and the notes within each group are sort of similar, but they're not identical. They're irregularities. And then, about halfway down the page, the bird got very excited about something. The whole different sort of pattern emerged, with longer bursts of notes and shorter gaps between them, but again, some pattern to it. Right? And there is utility in this, because there's a lot of information. If you just have a single beep, 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 there's no information in that at all, right? There's a beep. So if they could not communicate information just by something which has that much of a pattern. And if we were listening to it, I probably would think that sounds boring. It's not as exciting, but all these different sorts of notes and the different tempos and the different rhythms that come out of it, that's what makes it interesting. And so there's beauty in it as well, I would say. And so we need the pattern and the irregularity to generate some sense of beauty in this case. So, and realize then, and extend this to when somebody does something that you think is odd, but you don't, I'm not encouraging people to do things that are illegal, but legal things. Somebody does something you don't quite like, you don't quite understand, or maybe you find it a little bit irritating. Well, stop, think. Maybe there's something to learn. Maybe there's something interesting there. So, stop and think about patterns and irregularities in your dealings with people, as well as in your dealings with technology. That is all I have to say today.
Thank you so much, Professor Viney, for your time to share with us on your experience about pattern and irregularity in both technological part and also the beauty of it as well. Yeah. And from now, I'm open for any question that you might have about his presentation or about his experience in large varieties of field. You could type in the chat box, or you could turn on your microphone to ask question or to discuss with us and with him as well. Yeah. Meanwhile, while I'm waiting, in case you have any topic to discuss, I would like to share the woodlark sound a little bit. Yeah, I searched on eBird and then I found one. So just, yeah, I could share on my screen here a little bit. Let me pull it up. Okay, I think you all see it. And they have this part, listen.
Ooh. I agree.
Oh, high note, too high. Yeah, so that's one of the sound that the woodlark make. Yeah. So I think, yeah, it's the topic that Professor Viney share with us, right, about his friend that recorded, and it helped us to see that, oh, one really enjoy the nature, and one could really learn about their, not really, I'm not sure whether I can call language, but it's the sound that they make, right? Yeah.
Well, it is a language because they
It
are
is a language. Yeah.
absolutely a language.
Yes. So yeah, I can notice okay, this, for example, Oriental magpie, they're gonna make sound like this, and then the other type they make different sound. Yeah. for the different species of birds.
And on the subject of which I'm interested to see, I see a picture on my screen here. There's a shark, and the shark is saying meow.
Oh, you mean the profile?
Yes, there's a picture. It's
Oh,
near the bottom on the right hand side. It looks like a shark, and
oh yeah, I
the
saw
shark is
that
saying meow. So
from Marisela.
so
The profile.
so I think that is a creative irregularity.
True. Shark learn how to say meow.
Yeah. I also see two people have the same picture. It says absolute cinema.
Oh, let's see. Oh, Thanapat, no? Oh, maybe on the maybe he used two device. Yeah.
Two different student names, but the same picture,
Oh,
which is
really?
yeah.
Oh,
So,
I
so
couldn't.
you guys can see what I'm sitting here looking for patterns and irregularities in the pattern of names on my screen, and seeing what I can learn from it. So,
Mm.
I feel very privileged to be sitting in front of a group of such interesting names, and uh, but they're not asking questions.
Yeah. Anyone want to ask, or you could type in Thai and then I translate too. If like if you want me to help a little bit on like explain the question. Mm. Um, this one he might not talk about this today, but he also know many language. Yeah, he in case any of you studying language, um, you may also like discuss uh or maybe ask his advice too. Yeah.
This is something that you can. Something I tell my students here. Exactly this is international. Students don't always easily ask questions, so I think that's international. Here in the States, my students sometimes they sit very quietly, don't want to ask a question. But what I tell them is that, and particularly the older your professor is. So I'm in my mid-60s now, so I'm getting on a little bit in age. And what your professors have is experience of being students, being successful some of the time, because we managed to become a professor and keep our jobs and survive and enjoy it. In my case, I really sort of enjoy it. But we travel the world, we meet different cultures, we have thought about different problems and situations. So yes, we can answer things about that. So somebody has a hand up.
Yes, please turn
Yes,
on your
Professor.
microphone. Yeah.
Yes. One thing I want to know is that the as you mentioned, as I catch up, the materials have like irregularity, even though they have the same types of something. So like in the manufacturing process of something, is there like methods like testing how can I say before manufacturing whether a metal is well shaped or not, like that. How method did you use to like measure or something about the irregularity and make sure they are like good shape or good quality, something like that.
That is a good question, and there's no short answer, but um, there's an area of materials science called materials characterization. And so then you have to so you learn about a lot of techniques in materials characterization. And so the question is then where the expertise comes in is to match the technique to the question that you have about your material. So some of the techniques are chemical. You just simply want to know, and it is good for quality control to know in an alloy how much copper and how much silver or how much uh, uh, gallium is in there with the silicon, or arsenic in there with the silicon. So simply testing the composition. So those would be chemical analysis. Then there's a whole lot of techniques which look at the physical structure. So this could be something like X-ray. So you get X-ray, you get a pattern. Interestingly, it's called a diffraction pattern, and from the pattern you can tell actually all sorts of things: how perfect the crystals are, you use the right wavelength of X-rays, you can tell how big or small or what size distribution there is. You can use electron microscopy or atomic force microscopy, which will tell you about structure at different length scales. You can probe even the structure of the dislocations with an electron microscope. That's how they were first observed, actually, was with electron microscopy. And so you can use those sort of techniques for looking at the defects. There's a whole lot of physical property characterization. So is the material strong enough? Is it stiff enough? Is it tough enough? And so people like that actually tend to make quite a lot of money in what is called failure analysis, because in a real industrial process, something breaks, there is a problem. Something, money is being paid to for the equipment, and the equipment isn't working, and so money is not being made using that equipment. So people who can very quickly troubleshoot why something broke, fix it, and stop it from happening again. And so maybe the mechanical properties of the equipment wasn't right, or maybe it corroded. So people understand chemical failure, corrosion in other words. People understand mechanical failure. Why did it break? How did it break? And can use the right techniques on the broken pieces to go and figure out what went wrong. There's actually some very good jobs in that area. That's a short answer, but courses in failure analysis and materials characterization, that's where you learn all the different techniques and which ones are appropriate for particular questions.
Thank you, Professor.
Oh, you're welcome.
I have one thing in mind that I'm not sure whether it's actually applying or not. But in cases like when we're measuring something and metal is not like qualified enough to make something like it may be strong, not strong enough or pure enough. In those cases, I think they might also use that material in other cases, like instead of manufacturing one thing, they use it to another like things, or like they still use this metal and then like make the how can I say the product lifetime to shorter. Like for example, a good quality one can last example 5 years or something. In this case, when they use not good material, and then like might reduce the time to 2 to 3 years, and then recheck again and fix again, something like and think these kinds of cases might exist, but I'm not sure. And then do you know anything like that in the actual world using or something?
So one possible answer is the idea of what's called accelerated testing. So and this is particularly easy to do with some polymers. So what I'm going to describe here is I come at it from a knowledge of polymers. But imagine that you've got an aircraft component, and maybe it's made out of some sort of plastic, and you want to you'd like to be testing it on the ground and have it break before the one that's flying in the sky breaks. Okay, so if you can get data from something how long might be the failure time for this component, test it on the ground, but find a way to hurry it up so that it's guaranteed to fail on the ground before it fails in the air. And so there are processes called accelerated testing. So you can hurry things up with polymers by just doing the test at a higher temperature. So you give the structure some more mobility, so it goes and deforms more quickly, and so it will break. It will go through the whole process of deformation and failure more quickly than one that is going at a lower temperature. Or you might find maybe in a collision, you want to slow things down enough so that they happen slowly, so that you can actually observe them. So you can also do it like for impact testing. You actually do the real tests, the tests at a lower temperature, so things take longer. So it spreads out over a period of time that you can observe. And so you can look at failure analysis for materials, for collisions, particularly plastic materials, by doing the whole test at a lower temperature than the material would be implemented. So if you want to read more about it, find a book on polymers and read about viscoelasticity and time temperature superposition. Time temperature superposition.
Thank you so much. Can you please share about the book maybe in chat, because I couldn't catch up like the the one you said.
So what you would look, many textbooks will have this. I'll type in. So what you want to look up is the time.
Yes, Professor. Like, is there a like how can I say textbook? I want to know about the like analysis techniques or like some of the SOP. They trying to test the materials and then they reapply or how can I say they fix or something like that. Majority like analysis things.
I'm typing. I type slowly. So.
Yeah, thank you so much.
There's a textbook by the three authors that I've just put in there: McCrum, Buckley, and Bucknall. And I cannot remember the name of the book, unfortunately. So I remember the name of the authors, and because I know Professor Paul Buckley personally, that helps me to remember the name of the book. He was I taught at the University of Oxford for a few years, and he was a colleague in a department next door. So. Now this won't go into the SO. It's not going to go into the standard operating procedures. That because that's sort of at the level of application that I haven't spent very much time at myself. But the principles are here, and certainly the time temperature superposition principle, which is for static loads, and there's an equivalent also for dynamic loads. But this, you have a map and the starting direction here. You shouldn't get too lost.
Yes, thank you so much, Professor.
Very welcome. Well, so people do ask questions. This is good.
Yeah, it's good. So they could like have a starting point on learning about this topic. Yeah. Any other questions?
Finding a good lead is important, and then you start looking for patterns.
Yeah. In this case, I would say if any of you have other thing to discuss that you would like to discuss with Professor Viney, you could inform me, like either in live group or in the Zoom chat when we have class. But in this case, for today, I will say we could take photo together before we continue the activity in our class. Yeah.
Do you think we can get people to turn their cameras on?
Yes, please. If you could turn your camera on, please do, so we could take photo together. Yeah.
And do take up the offer. If you have questions related to what we talked about today, then Vipari will collect questions, and we could reconvene at some point, or I can, she and I can have a Zoom meeting and we can discuss whatever works efficiently. So, we have people. We have more faces than we did. Oh. Hello. Ah, three people on one of them. There we go. Right, it's all happening. Good. I appreciate being able to put real faces to names.
Yeah.
Good. Oh. Good. Good. I'm also doing a screenshot from here. So. All right. Looks like a game called Celebrity Squares now.
For Chayanese, the screen you could lower that. Yeah, like that. Okay.
I still see a shark that says meow. That's so much fun. All right.
Okay, I'm going to take the first photo. Yeah. 1, 2, 3, cheese. Okay, the other one, because there are 2 page. Okay. 1, 2, 3, cheese. Okay.
Let me see
Anyone
if I
want
can
a screen? Oh, you have what? Oh, the
I'm going to see.
occupy.
I
What
just,
is that?
it's a hedgehog.
Hedgehog. Oh, hedgehog men.
Let's see.
Okay.
Let me just see if I can do it. It's difficult because it doesn't always appear in the
Oh, with background. Yeah, I think with background.
the camera can't decide if to look at me or the hedgehog. So
Let's see.
there we go. There we go. Oh, I've got to stare at the. There we go. Ah, disappears again. Yeah, got it.
Okay.
Thank you.
Yeah, thank
Much
you, Professor
appreciated.
Viney. Yeah, thank
Well,
you so
have a
much.
good day. Have a good class, and thank you. Thank you for letting me talk with you. I've enjoyed the experience. Cheers.
Thank you. I will continue to share the activity today, okay, and also give you some example. As I mentioned, it will be group of 2 to 3 people, so you could discuss with your classmate, okay? And let me find a slide first. It's over here. Okay, let me share my screen now. Okay, here we are. And then I will send you this slide on Line group as well. Okay, you all can see right now. Okay. Let me stop record first and then I will re-record the other one.